Hello all, in this video we're going to look into the derivation of the rate of change of a quantity integrated over a volume. So before all that, let's look at Leibnitz theorem. So suppose we have a time derivative of an integral whose limits are changing in time. So from undergraduate calculus we know that this is equal to over a to b plus f at b db dt minus f at a dA dt. The physical interpretation of the problem is clear, that if we have x and y axis like this, and if the initial function is like this over the limits a at t and b at t, if the function after a time delta t moves over here and the limits are moving over here, okay, so in this case the initial area was area A, B, C, D, while the final area is P, Q, R, S. Okay, so we are supposed to find out the rate of change of the area. So essentially it is area of PQRS minus area of ABCD by delta t. But so area of PQRS minus area of ABCD excludes this volume. It excludes this volume. So the numerator consists of the following terms. It consists of A, B, Q prime, P, a loss of area, this area is lost. Okay, it involves a gain in area equal to Q prime Q R C. If I draw it like this, and this area is gained, and appropriately area DCRS is also gained. Okay, so area DCRS is equal to B at t plus delta t minus B at t, this is the base, multiplied by the height. Okay, so the height by mean value theorem is equal to the value of function at C or equivalently value of the function at R, but since we take the basis at time t, we have the value of the function at B. Okay, similarly the area lost A, B, Q prime P is equal to A at t plus delta t minus A at t, this is the base. Okay, this multiplied by F at A comma t. Similarly the area that we gain Q prime Q R C is essentially the integral f at t plus delta t minus f at t. dx over a at t plus delta t to b at t. This is equal to integral of a at t, b at t, del f del t delta t dx, where we have replaced the limit a at t plus delta t by a at t, because we eventually take the limit delta t tends to 0. Moreover, we have used a Taylor series expansion for f of t plus delta t, essentially, which is equal to f of t plus del f del t delta t, and so on. This, if we substitute over here, we obtain only this term. So this is equal to integral a of t to b of t del f del t dx times delta t. So using equation 1, 2, 3 and 4, the change in area is equal to this term minus this term plus this term. So look, b at t plus delta t minus b at t times f at b comma t minus a at t plus delta t minus a at t times f at a comma t plus integral a to b del f del t dx delta t. This is the delta area. This is the delta area. Okay, so delta area by delta t is therefore b t plus delta t minus b t by delta t. We take the limit delta t tends to 0 times f bt minus a t plus delta t minus a t by delta t f at a t plus integral a to b del f del t dx. So in the limit this becomes db dt, this becomes f b comma t dA dt f a comma t plus integral a to b del f del t dx. Okay, so this completes the proof of Leibniz theorem.